In this lesson, we're going to look at an alternative way of expressing complex numbers. So far, we've been expressing complex numbers in Cartesian form, where we write them as z equals a plus bi, where a is the real part and bi is the imaginary part. That's called Cartesian form, named after the mathematician Descartes. Today, we're going to look at how to write a complex number in modulus argument form. So the modulus is the distance away from the origin that the complex number is on the Argand diagram. The argument is the angle that it makes with the positive x-axis. So we're going to look at how we can express numbers in that form and how we can convert between Cartesian and modulus argument form. So this is the complex number z equals 3 plus 2i. We've plotted it on an Argand diagram, 3 across and 2 up. Currently that's written in Cartesian form. We're going to look at how can we convert that into modulus argument form. So the modulus, we use the letter r for that, is the distance between the origin and the point on the Argand diagram. So in order to find the length of that line, r, we're going to use Pythagoras' theorem. So the easiest way to do that is to actually draw a right angle triangle on your diagram. There's the right angle. See, the base of that triangle is 3, the height of that triangle is 2. So we're actually using Pythagoras' theorem, c squared equals a squared plus b squared. In that particular case, it becomes r squared equals 3 squared plus 2 squared. So the modulus of that complex number becomes r equals the square root of 3 squared plus 2 squared, which works out as root 13. We're just going to leave that as a surd because it's easier to deal with than writing it as a decimal. We now need to find the argument. Now the argument, we often use the Greek letter theta for that. It's the angle that you have to turn anti-clockwise, starting from the positive real axis. So from positive real numbers, going around anti-clockwise till you get to point P. So to find this angle, we're going to use trigonometry. So base is the adjacent side. Put the adjacent on there. The height is the opposite. So in order to find the angle, we're going to be using O and A, so it's going to be tan. So we are going to be using tan theta equals opposite over adjacent, which is 2 over 3. So theta is going to be the inverse tan of 2 over 3. Okay, so one decimal place on your calculator, inverse tan of 2 over 3 is 33.7 degrees. So that is the argument of that point. So here are some general notes on that. Generally speaking, a complex number is written in the form z equals a plus bi, that's Cartesian form. We can find its modulus using r equals a squared plus b squared square rooted. An alternative notation that's sometimes used, instead of the letter r, we sometimes put lines around the z, vertical lines. We either say the modulus of z or we just shorten that to mod z. So the argument, we use the letter theta for that. Now it can be found using inverse tan of b over a, but you do need to be a little bit careful with that because that angle is defined as the principal argument between minus 180 and plus 180. And to make sure you don't make any mistakes with the angle, it is always a good idea to draw a sketch and actually look at the angle on the Argand diagram and decide, does that look like a sensible answer? And if not, you can use some calculations to work out the correct one. I'll do an example of that in a minute. An alternative notation for arguments is that we can just use the word arg. So arg z just means the argument of complex number z. And we can also convert z equals a plus bi into this form. We can write it as z equals r bracket cos theta plus I sin theta. R is the number that you've just found for the modulus. So in the previous question, r would be root 13. Theta is the number that you just found for the argument, so it would have been the number we found on the previous slide. Similarly, the complex conjugate z star, that's written as a minus bi. That can be converted into r bracket cos theta minus I sin theta. So this is an example of how to convert a complex number from Cartesian form into modulus argument form. Give you a second to write that down, pause the PowerPoint if need be. Okay, so we're going to start with the complex number z equals minus 2 plus 4i. We're going to find mod z and arg z, and we're then going to write z in the form r cos theta plus I sin theta. So, first of all, the modulus can be found fairly easily because we know that the formula is just a squared plus b squared all square rooted. So to find the modulus of z, we could just do 2 squared plus 4 squared square rooted. We don't need to worry too much about the negative and negative 2 because obviously when you square a negative number it becomes positive anyway. So if you simplify that, that becomes 2 root 5. So the value of theta can be found using the inverse tan formula. But we do just need to be careful, because if we just sub those numbers in, theta equals inverse tan of 4 over negative 2. We get a negative argument. No, that's fine. Arguments can be negative. They can be between minus 180 and plus 180. But we now need to just quickly check and say, does that make sense if we look at a diagram? Does that look as though that is the angle? So if we were to plot z equals minus 2 plus 4i on the real and the imaginary axis, that point would go up in the top left quadrant. Now we know that the argument is always measured from the positive real axis, which is here, and it always goes anti-clockwise. So just looking at that, it doesn't make sense that that complex number would have an argument of minus 63.4 because the angle we've drawn there is not 63.4. In fact, minus 63.4 is in the opposite direction. Okay, so by drawing a diagram, you've highlighted that is not actually going to be the answer. We need to do a little bit more calculations to work it out. However, we can use the fact that because it's the exact opposite direction, that those two lines make 180 degrees. So altogether, those two angles combined make 180 degrees. So if we've got 63.4 below the real axis, we must have 180 minus 63.4 above the real axis. Or minus 63.4, add the 180 on. So the argument of z is 116.6. That makes much more sense because when you look at the angle that we've drawn, it does look as though it's obtuse. It looks as though it's bigger than 90 but smaller than 180. So 116.6 falls within that range nicely. So therefore, if we wanted to write z equals minus 2 plus 4i in the form r cos theta plus I sin theta, we can do that just by putting in 2 root 5 for r and 116.6 for theta. So z is 2 root 5 bracket cos 116.6 plus I sin 116.6. So finally, here are 5 complex numbers in Cartesian form. I'd like you to draw a sketch for each one showing where they would be on the Eigen diagram and then convert them into modulus argument form using Pythagoras and trigonometry. And then finally write each of the 5 complex numbers in the form r bracket cos theta plus I sin theta. I'm just going to show the working out for question C on the previous questions. So we wanted to convert minus 2 plus 7i from Cartesian form into modulus argument form. So the first thing we do before we start is to sketch an Eigen diagram and to plot the point minus 2 which is here, plus 7i here, real axis, imaginary axis. That is the point there. Just going to draw a line from the origin to that point. So we're going to be looking for modulus and the argument. So the modulus is quite straightforward because we just need to find 2 squared plus 7 squared square rooted. So r is going to be 2 squared plus 7 squared square root, which is root 53. Now the argument, if we look at the angle starting at the real axis, positive real axis, going around anti-clockwise, you can see that that angle there is greater than 90 and smaller than 180. So we know we're looking for an obtuse angle, a positive angle. So there are several ways that you can calculate theta. One of the easiest ways, to be honest, is to calculate the angle on the other side. So if I just draw that on there. Let's call that angle alpha. Now if we find that angle first, we can then see that theta and alpha, that they make a straight line, so they add up to 180 altogether. So in order to find alpha, I'm just going to change this into a right angle triangle. I can see the height of that triangle is 7 because of the 7i. So the base of that triangle is 2. I'm just going to call it positive 2 because lengths are always positive. So that's the base of the triangle. So if we wanted to find the angle alpha, we could say, right, well, 7, that's the opposite side. And then 2, that's the adjacent side. So we're going to be using tan. It's nearly always tan with these kinds of questions. It's always opposite and adjacent. So we're going to calculate tan alpha equals opposite over adjacent, which is 7 over 2. So alpha is going to be the inverse tan 7 over 2, which is 74.05. So if we just round that to 74.1 degrees. But remember, that's not the angle we need. The angle that we need is theta. So in order to find theta, we're going to do 180, take away alpha, 74.1, which is 105.9. Let's round that to the nearest whole number, that's 106 degrees. Okay, so that's the theta. That is where the answer to C has come from. So this is the answer to question D from the previous set of questions. I'm going to convert -4 minus 3i from Cartesian form into modulus argument form. I'm going to start with a diagram. As I said, it's always best to draw a diagram with these questions because you can see immediately if your answer doesn't look right, especially for the angle. So -4 in the real direction is there, -3 in the imaginary direction is there. So the point that we are looking to find is in the bottom left quadrant. So we've got R. Now, sometimes a question will ask you to give the argument between -180 and plus 180. That's what we're going to do here, which means that the angle we're going to find is actually going to be negative because it's below the real axis, it's going clockwise. However, just be aware that in some questions, in exam questions, for example, they might define the argument as being from 0 to 360. If that was the case, you'd have to go around the top. So if it was from 0 to 360, you would have to go around the top here. But in this case, we are going to go clockwise. So because the argument is usually anti-clockwise, we're going to end up with a negative answer in this case. So we're going to find R first, that's the easy one. 4 squared plus 3 squared, square root. Okay, that is just 5, so R is 5. Now to find the angle, again we've got several different choices. I think probably the easiest way to do this one might be to find this angle here first. So again I'm going to call that angle there alpha. Now to find alpha, I'm just going to convert that into a right angle triangle. Just need to find the length of the two sides. Now this side here is 4. I know that it's -4 on the diagram, but because lengths are always positive, I'm just going to use the number 4. And then the height of the triangle is 3, again because lengths are positive. So to find alpha, That's your opposite side. That's your adjacent side. And use tan. Tan alpha equals opposite over adjacent, which is 3 over 4, which means alpha is the inverse tan, 3 over 4, which is 36.86, so we'll round that to 36.9. Now, in order to find theta on the other side, we're going to do 180 minus 36.9, which is 143.1. But because we're just going to go to the nearest whole number, just going to go for 143. However, we need to then look back at the diagram again and remember that conventionally the argument is always measured anti-clockwise from the real axis, positive real axis. Because this angle is going clockwise, it's going in the opposite direction, the argument of that complex number is negative 143. So although the angle itself is 143, we need to say that the argument of Z is negative 143. So that is where this answer here has come from.